Hi, I'm Rohit. I'm an ML infra lead at Nauto, working on many different projects. Today in my talk, I'm going to be talking about one very interesting project that I have been working on. This involves merging time ranges using an online algorithm in a very fast manner. And we back this algorithm up by Scylla as our database solution. Then we apply this method on our IoT platform, where we gather data from many devices in the field and understand driving behavior, as well as trips and how the drivers have been driving. Hey, I'm Rohit. I'm an ML engineering lead working at Nauto. And yeah, previously I've worked at different places like Google and other startup, and have a background in machine learning and running computer science from a few different universities. So what do we do at Nauto? We have this device that we install in a car, and this device collects in turn snapshots from inside the car, snapshots from outside the car, and it has sensors such as an accelerometer, a gyroscope, and so on. Using this data, we understand driver behavior and know what good driving means, and who is driving well and who is not driving well. In turn, we sell this as a product to fleets. Fleet managers know who are the good drivers, who are the bad drivers, how they can coach drivers, how we can just make driving safe for everybody. So in order to do this, there are two core pieces of infrastructure or systems, if you will, that we need. First, we need to understand what a trip is, when the driver started driving, when the driver stopped driving. Second, to know who the driver was in the car without having the driver themselves say, hey, it's me, I'm so-and-so driving the car. So towards this, we upload snapshots of the driver, and we also take the GPS information, as well as whether the vehicle is moving or stopped, and some other pieces of information, and pass it to the cloud. Now, in this talk, I'll focus on one of the things, which is building the trips or merging time ranges and going from there. The driver recognition part is coming using machine learning techniques based off neural networks and so on. We wished we had some blockchain also, but we don't have any blockchains. So how does the flow look like? We start by gathering GPS information and vehicle states, such that if the vehicle is moving or if the vehicle has stopped. And then we batch it up on the device, constructing some small trips or trip segments, and send them up to the cloud. On the cloud, we have an ingestion service running that receives this data, and it posts it to Kafka, sharded by the device ID or partitioned by the device ID. We have a bunch of workers ingesting data from Kafka, such that every single worker is basically getting data from the same device. So data from the same device doesn't go to two different workers. Within each worker, which is a binary, we again have a sharded worker pool. So it's the same thread always that is getting data from the same device. Now, why do we do that? When we do that, we don't have to use locks, and we don't have to deal with concurrency issues and so on. We have the luxury of just having one thread deal with all the data. When we get these trips, or these micro trips from the device, we look at what the neighboring trips are in Scylla, and then we generate a merge trip and save it back. Now, the reason why we had to use Scylla was just the amount of load or I/O operations that we would put on Scylla when we are running at scale is, let's say, too expensive for any other system, and sometimes a little difficult also. So here's an example of a trip. We broken into 3 segments, and they are not combined together. The way we define trips is if there's a gap of more than, let's say, 5 minutes, they are different trips. And in your case, whatever time ranges you have, you can have a different definition of when a time range is actually continuous and when it should be split apart. Here's someone driving on 237 coming to our office, 3 different segments of this particular trip. In order to do this, we have one of the schemas that we deploy, which is called the device trips table or the time ranges table. It has the ID as part of the partition key, which is our device ID or the vehicle ID in our case. The bucket, or in our case, it's the day bucket, which is gathering all the data for that particular device for that day. And this is to make sure that your partition sizes are manageable and they don't grow too much. Then we record the end of the trip and the start of the trip and of the time range, and that forms part of our clustering key. We have version. This is basically something that we use to be able to run multiple versions of an algorithm or run experiments and do testing at the same time. And then we have a structure which we call details, and in our case, we are using a protocol buffer and saving all the additional metadata about the trip, the GPS routes, and so on within that. Now that we have JSON, maybe we could also try using JSON, but we haven't tried that yet. Finally, the key that we're using. So as part of your main partition key, we have the version, the device ID, and the bucket. And the clustering key is your end time and the start time, note in that particular order. And this order enables us to get the trip that has ended the most recently very fast. And this optimizes for the most common case where most often your data is coming in a sequential manner, and for those one-off cases where you have had outage and you have to replay some data, or someday the device woke up after some time and sent some old data, we can handle it through different means. So here's a key thing to remember, and what really lets this algorithm work really well is whenever you are using a sharded worker pool or the kind of device-based sharding that we are doing, then we don't really need locks. And the chances of race conditions are practically non-existent. And I'm not saying they're never going to be there, but they are practically non-existent. And so as a result, whenever you look up a particular timestamp and there will exactly be only 2 trips or 2 time ranges, one just before and maybe one just after. And so looking up for 2 in the ideal case is enough. Sometimes just to accommodate that one-off case where it can happen, you probably want to look for 3. And I'll show what happens there. So let's take an example. Here's a trip recorded from 8 a.m. to 8:12 a.m. And this is saved down into Scylla. Next, we get a trip from the device. This is going from 8:40 a.m. to 8:55 a.m. And in order to, before we save this down to Scylla, we look at, OK, what is the trip that just ended just before? What is the trip ended just after? So if you think that I want to look at all trips that ended after 8:35 a.m. and all trips that are starting before 9 a.m. Within this particular range. Now, if you take the principle, you will realize that I don't need to do the second lookup. I only need to do the first, I just need to apply the first constraint, which makes it much more efficient. So since there was nothing, we save this trip time range down to the database. Next, let's look at another one that has come in. So this one using our definition of what is an overlapping time range, it overlaps with the trip that is just before. So we look up, okay, what are the trips that have ended just after 8:10 a.m. and give me the first 3 trips that are there. And of those 3 trips, only one really overlaps. We merge it with that particular trip, generate the merge trip, save it down onto Scylla first, and then delete the trips that were used as part of merging. And the reason to do it in this order is that just in case there's a failure before you have been able to save, you don't want to lose some data. At the max, what will happen is that you have a duplicate trip, which can be cleaned up in the next time whenever another message comes at that point. And this describes that almost condition, where you may have more than two time ranges or 2 trips to merge. So save that onto Scylla, and that's basically how this algorithm works. We use Scylla in order to do this. We have about a 3-node cluster. We put it in 2 different regions for privacy-related laws and so on, and pretty much using similar mechanisms as everybody else is using to set up and monitor Scylla. So that's it. Here's the rest of the team. And there are many more people who have contributed to this work who are not mentioned on the slide. Some of them also here.